Okay, so yeah, we're going to look at what a robot is made up of, or what makes up a a robot. Um, Again, we won't want disturbance. We won't want multiple mics to be on at the same time or noise from background. So let's just all comply. Now, first of all, Saka is the person who brought me here, so I feel it is necessary to actually appreciate him. So he's a friend and he has given me this platform to address RAIN-LAUTECH. Now, a little bit about myself. Basically, today I'm going to be speaking at RAIN-LAUTECH, and I actually appreciate the the honor to be here. So, without much delay, let's go straight into our topic for today. Okay. Now, when you say what makes up a robot, I believe this is something everybody can Google. This is something you can see everywhere. There are some key things that we know. Okay, yeah, when we see it, we know this is a robot. The structure, what it looks like, the actuators that actually move it. Then you know it has some form of sensors that collects data. Then we know we have something like a control system. A control system, more or less, is like the brain. We have the power source. Apparently, something has to power the robot. If it moves, something is powering it. If it does any form of actuation, there's some form of power. Now, we also have an end effector. You don't just want something to move, you want it to at least achieve some form of goal. If it's for automation, say for example, fabrication of cars, where you need to weld, your end effector might be a welding gun or whatever. Now, communication is key in robotics, and this is more like an introduction. As we actually go on, we would see that there is a lot of relationships between all of this. Now, when I was thinking of how to actually present this, there's something people normally tell me. They request for general robotics, like generally what makes up a robot. But the truth is, robots are extremely specific. So there is this general structure, yes. There's even an ISO standard and a definition by IEEE in 2009 that fully defines a robot and the terminology. We all know that. But if we are doing something like this, I would prefer we actually go into the actual robots and see what we have for ourselves. Now, I decided to start with quadruple robots. These are those robots that you see that looks like dogs. Now, we are going to make reference to every single structure, the 7 structures that we've put up here. We talked about structure, which is the body. So I'm very sure if you see a dog, you know what a dog looks like. And then if you see a human being, you know what a human being looks like from just the body. Now, this is the first structure. If you see a dog, a robot dog, you know that's a robot dog. If you see a humanoid, you know it's a humanoid. If you see an autonomous vehicle, you know it's an autonomous vehicle. Barely from just the structure. So now you can say that is now a core building. Yeah, your hands are raised, Osanyade. Okay, I'll. What does it?
I think you should continue. You take the question and answer session
Oh,
after you're
okay,
done.
okay. So like there's a question and answer. Okay, okay, okay. Okay. Usually that's not my style. Usually I answer questions on the go. Okay, so there's a question and
Okay.
answers. No, 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 no. If that's the formation, there's a question and answer session. Then I would play by your rules. Um. Okay. So as I was saying, now you can see structure is a core building block. Structure now, if you see an underwater robot, you can tell from the shape. In no place would they use the shape of an underwater robot for a drone. Underwater robots naturally self are made to be negatively buoyant so they can sink. A drone is supposed to be as light as possible, so it floats, so it's like flies. So structure is a key player. Now actuators is how do they move. So you see a dog moves on all four. A human being moves on all two. A car, 4 wheels. depending on the variation. So now, how they move now is another signal to tell you that, okay, this is a fundamental block. And if it moves so way, it is so robot. Sensor now is what they collect. Um, say for example, you are doing inspection, say inspection of underwater pipelines. The type of sensors that you would equip the robot defines what it's going to do and what it cannot do. Now, I'll give an example with force sensor. Force sensors are those sensors that you can use to grab something and you can predict how much force you are holding so that you know whether you are actually gripping or you are still loose. So force sensors are completely useless on drones because there is almost no reason why you would want to fly a drone and have a force sensor. But if you put a force sensor on a robot arm or a robot hand, you can tell that, okay, you want to be able to tell how you are gripping and how strong or how loose. So sensors are things that also characterize robots. If we move on to the next slide, we see control systems. If I tell you, most of the control systems are like the most common ones, Arduino and Raspberry Pi. There is a robot arm that uses one Arduino. But you see Unitary Go 1. Unitary Go 1 is that robot dog by Unitary. It uses 4 CPUs. It has an ARM CPU, and then it has 4 other NVIDIA CPUs. Why? Now you can see that there's a lot of computation that is needed for that kind of robot. Whereas your Arduino robotic arm, you really don't need much. At most, you are moving 4 motors or 5 motors. So you do not need much. Now the power source is still what you would use to know what kind of robot, like what building block and things like that. When you talk of power source, it's basically what supplies the electricity. Some might be electricity. Bigger robots might even use hydraulics because hydraulics delivers a ton of force. Some other robots might use air. There is this MIT robot, very small, soft robot. It uses pneumatics, just air pressures and valves to move around. So now that we have a little bit of background understanding, let's look into something um a bit more specific. So I'm going to show a little demo to drive home some points. Mm, okay, so the idea ultimately is so we can see these robots and see what they look like and see what their forms look like. If possible, see the sensors that we have on them. The first one we are looking at is from our slide is our quadruple robots, which is 4 legs like the dogs. Usually they have 4 legs clearly, some 2 to 3 joints, and then actuators are done by motors or hydraulics because they need a lot of power, a lot of torque actually. So if we get here for our quadruples, all right. The reason why I'm bringing this here is so we'll be able to actually see and identify what really makes up this robot. Now, this particular robot, now you can see clearly you have a limb. There are 4 limbs actually. Each of these limbs have motors on them. So I can basically turn up the calf because of a motor that is present on this particular joint here. That's what allows me to be able to do that. Now, at the same time, the hips can also be moved. Let's use this hip instead. You see the hip can also be moved. The reason why that hip can also be moved, it's simple. there is another motor up here. So by the time we actually move these hips, we find out that, okay, yeah, there's a motor that is turning there. Now, the two things that we have seen is an intersection of structure and actuation. We've seen an intersection of structure and actuation because the structure is the leg, the motors is the actuation. Going back here, if we come to the front of the robot, we can see some things that looks like cameras. These are stereo cameras. Would come, if we have enough time actually, we'll come to stereo cameras too. Stereo cameras, basically, they are able to see not just video but depth. What I mean by depth, they can estimate the distance from the camera to the object. At the same time, they can estimate the depth of the object, meaning the distance from the object to probably another object. So this now is on the head of the robot, which is intuitive. It's common sense because even the dog, the eyes are on the head. However, there are about 4 more cameras still along the body, although I don't think it's shown on the model. Now, basically, you can now rotate or you can send commands whatever way. So if we come back to the here now, we have our actuators, we have our powers. Electric motors, I've explained what electric motors actually do. Now the rechargeable battery pack, the rechargeable battery usually stays inside this midsection. That's where we normally have our rechargeable battery. So now we have sensors. If the robot cannot sense its environment, it cannot carry out anything at all. I mean, it's just like you can only give it commands, but it cannot respond. It cannot give feedbacks. So it's not a closed control system. It's more like it's open. You're just giving it command and you're watching it do things. So now we have an IMU sensor. And an IMU sensor is used to, inertial measurement units, it's used to tell orientation. So if, for example, it's bending in one way, the IMU can tell the control system that, hey, you are tipping one way. And control system will now probably rotate one of the legs to like balance it. So these are things that sensors do. Joint encoders also check precise angle, motor angles. We have foot contact for force and all of that. Then the vision I was telling you about, cameras, ultrasound, LiDAR, and the rest of them. If we look at this quadruple now, this is one of the pictures where we have taken out the upper shell. And outside this upper shell, once we move this upper shell, there's a lot of electronics. Now, this is the first time I'm going to make direct reference to the electronics being used because I wanted you to see where all those electronics are actually hidden. If you look at this robot here and compare it to the one we have up here, you would find out that the motor that is responsible for this movement is actually, you can probably see the motor around here, this point. And that motor is all controlled by this brain that is put in this compartment. We'll still come up to that side. Now, this is what I call the control system, or what is called the control system, the brain that we've been talking about since. Now, this diagram, if we take our time to look at it from left to right, we see stereo cameras, 2 stereo cameras. There's another stereo camera, and there's another stereo camera, and an ultrasonic. So we can see that these cameras up here and these cameras, there are also cameras that are down there. These cameras actually rotate pretty fast. So all these cameras somehow take feedback and send it to this belly, because this is where the main electronics are, the CPUs and everything. So from here, these cameras send it to nano. Nano is a kind of processor. It's the processor that Unitary actually uses, and then this is an ARM controller. But we're not fully specific on the details of that processor, which actually makes sense. And then we see that it has its own storage, 4 gig, and then 2 gig. This is like the RAM and everything. Now, all this is somehow connected to an Ethernet switch. Why? This is where this part comes in. Communication. Remember, we said we have structure. We've talked about structure. We have actuators. we've talked about the sensor, we've talked about control, or that's what we are talking about. We've seen power, and now we're looking at communication stroke interface. It allows data transmission or data exchange between robot operator and other robots. There's Wi-Fi, radio, Bluetooth. In this case, none of them, it wasn't Wi-Fi, it wasn't radio, it wasn't Bluetooth. Basically, it's running Ethernet. So this is what now controls everything, like connects everything together. Another thing that I would also want us to draw, like to look at, is we see something called 485. 485 is it's a connection protocol. For probably those that are conversant with embedded, we have UART, I2C, and then there are a lot of connection protocols with their advantages and disadvantages. But there's a reason why I am pointing out 485. 485 is one of the it's one of the ingenious ways, like one of the nice ways I've seen for communicating, like in a robot. Imagine now, for example, if I show you here, this is control. There are about 1, 2, 3, 4, 5, 7, 8, 9, 10, about 15 different motors you can control, or 15 different signals you can give. You want your signal to run in real time. Real time means as you send, it receives. And as you send to all motors respond at the same time. You try to reduce latency and all of that. In a bid to do that, if you try doing with normal slave master, where you talk to one slave first, you respond to another slave, you probably won't be able to achieve real time. So 485 is capable of sending to 32 devices with one line using differential signaling. But that is like another thing on one side. But this is something that is actually one of the smartest things about quadruple robots, or about the basics of robot communication. Now, the computer on board does some basic things like inverse kinematics, balancing control, and then it runs algorithm for posture and all of that. Because depending on how you actually orient all of this, say you just orient it, however, depending on how everything is, that's how you actually get your posture. And we started with a very bad posture, hence the fall and all of that. So there is also there's this video, probably if you probably want to see the slide, how you see the robots in action and the control system and how it's actually moving. Okay, so this is the demo that I've actually showed. I started with the demo actually. Now, moving on from quadruple, we have area robots. Area robots are more popular, drones, because it's easier to buy a drone than to buy a robot dog. Drones are also more practical for now than the robot dogs. So for aerial, it's a different kind of thing, but again, the same setup. If you see an aerial robot, you see a drone, you can tell that that's a drone. Why? Structure. Structure is the first giveaway. That's why it's always number one. These are the building blocks of robots. So now the structure is lightweight. It has quadcopters. There are other drones that have far more. Some have less. Some even have wings, depending on configuration. So now we've gotten structure out of the way. We know this is our robot. The next thing we'll now look at is propulsion. Propulsion is actually actuation, how to move it. The only reason why I'm using propulsion here is propellers. When you talk about propellers, you just liken it to propulsion, that kind of thing. Else, it's the same thing as actuation. And for the actuation of a drone, our idea is not just to send, because you look at this now, in this one, you send motor signals and it moves a type of way. It moves a type of way. But for the propeller is continuous. So now you're saying that not only is there difference in structure, but now there's difference in how they move. The propeller would not just turn a certain angle and stop, or it will not just rotate and stop. The propeller would continue spinning. Now, for the propellers, we have motors, DC motors, brushless, that actually control them. There are some motors that can spin in both directions. There are some that the propeller has to pitch, but again, That's complex configuration problems. We now have what is called an ESP. So because, say for example now, here, I can easily move my joint to, say for example, I can move my calf to almost 90 degrees or almost 270 degrees. I can easily send that, like it's easier to give that kind of command here, and you know how it's moving. And then you talk about the propeller now. How do we now give its command? For the propeller, you give speed, and then that speed has to be translated into power or current that is being sent directly to the motor. So for this now, that's what the ESP actually do. So it allows us to write high level code rather than manually writing the code that turns the propeller. That's for propulsion. Now for power we use high energy lithium polymer batteries. These powers are similar to the one on the robot dog, but the one on the robot dog is usually far bigger. And this particular one has more emphasis on current because the motors are low, they are low voltage, but they need a lot of current to be able to generate that thrust. So this kind of batteries will like more focus on current than on voltage. Another thing we now look at is this IMU. Now for aerial robots, you would usually have your computer and then you would have a flight controller. This difference falls under what? This difference falls under control systems. Control system. Now you can see now that as for the quadruple, we had 4 computers. And that 4 computers is not because of the 4 legs, actually. I explained why we have 4 computers. So it's not as if it's because of the 4 legs, no. But for the drones, we mostly have 2 computers. One that is going to handle high-level tasks, autonomy, as we say, and one that to actually handle lower-level tasks like sending motor. Say, for example, you want the drone to go forward. For a drone to go forward, the the um the first two, the revolution of the first two will drop a bit. The revolution of the last two will increase a bit, and then the drone tilts forward and move forward. We don't want to be the one to write that logic ourselves. So all we write is move forward, and low level just translates it for us. So that is the difference now in things. So we look at navigation and autonomy. I've also talked about autonomy, having the higher level and then using GPS and things like that. Communication is something we must always cover. In terms of communication, as you can see on the quadruple, most of the communication was like internal because it's easy to control everything like internally. But for drones, there is no use case for a drone if the drone remains on the ground. There is absolutely no use case. So it has to fly. And the moment you give that kind of distance, you actually need to be heavy on what you're using to control it. So radio signals are usually the best. And then we also have telemetry if you want to make it go autonomous. And if you're making it go autonomous, you give it some form of location or ground truth for it to be able to return back to where it is. For the control software, on the robot dog, I didn't go into the control software because that's a bit closed, a bit how do I put it? It's proprietary, right? So on these drones, we have a lot of open softwares. We have Autopilot, we have PX4. Then that's your normal Peacocks or something. So basically, what they do is they help with, you see that low level thing where you want to move forward and then it speaks to the, that's what they do. It's literally firmware kind of thing. And then you just focus on writing higher level codes. Now, I've not given a demo for, I think the demo for the drone is a bit different. Okay, so for this drone, I have something set up. This is the drone, yeah, and it's a simulation, meaning this is actually how it would move in real life, roughly. And this drone is made to follow a circle. So let me demonstrate something about control systems. The drone is moving in that circle because I have set a controller to ensure that the motors retain that circle, that radius of that circle. What happens if I grab the drone and bring it down? It goes back. Now, that dragging is disturbance. The drone automatically goes back because there is an existing control system on it. I can choose to like take it out a bit. What control environment is this? It is pi bullets. So I can choose to, yeah, but because it's a simulation, it has to be realistic. If a very strong wind takes that drone elsewhere, yeah, school, I mean, the game ends. The game ends. So the drone tries to recover. The drone will try to recover multiple times, but it just can't. So that is about the drone. I mean, that is one way to go about it because I wanted it to fly. Yeah, I'm not using this for the drone because this is extremely computer intensive. Like my laptop is actually lagging and I don't want to run a simulation while on the call. Okay, so back to the slide. Now, there's something I love, which is, oh, okay, so this is the data. It plots data for me, which is irrelevant for this class. So there's something I also love about when they say types of robots. The first thing I would love to mention is swarm robots. But that's because swarm robots is not one robot. It's a it's a group of robots, right? And when you talk about swarm robotics, what comes to people's mind is a lot of robots. But how I see it is they are all one, right? So this is how I put it literally. In swarm robotics, intelligence isn't centralized. That's true. If it was a single robot dog, it's one person, it's centralized. I mean, I agree with that. It's distributed, meaning the intelligence is on a lot of robots at the same time. Fine, but they are one. And I would draw my illustration to a flock of birds flying and a school of fish. So these flocks of birds, they move in so much harmony that you would know that, okay, yeah, as one is as it seems as the first one like pitches upward, the rest can pitch upward and like they're all moving together. So we have hundreds of simple drones that act together as if they are one, and that's swarm robotics. And I've decided to like add that so that you see we'll now compare it to a single robot and see how is swarm robotics actually a type of robot that we can use the core of a normal robot to explain. So yeah, this is my experience with swarm robotics. This was in Prague, and we had a lot of robots. We had a lot of drones, and we did some pretty some pretty complex stuff because this was GNS denied system. Long story. If you can actually see the picture, you will see that there's a drone with a lidar, and that's like the first time I'm seeing a lidar on a drone because the lidar is really big, and then it's a quite big drone. Okay, so this was actually the project we worked on. It was cooperative motion planning. Yeah. So this is what we're looking at: structure. Again, when you see the structure of swarm robotics, you will know it's swarm robotics. By the time like 10 drones on the fly for air, you know that, okay, yeah, that is a swarm. So that's the structure. Now we're not looking at one, we're looking at a lot of them, right? If one of the drones maybe spirals out and loses, say it falls, you have 9, the swarm still remains, right? Until all the drones actually fall and maybe there's one left, then you can say, okay, it's no more a swarm. But if you have two drones that are still up there, I can still call it a swarm. So yeah, that's the structure. Now the frame design, well, in this case, there is no physical frame. So the frame design would now inherit from the um the actual drone, right? So the frame design of the swarm robots is, so you can have a swarm of dog robots. Yeah, you can have a swarm. It's something that some people are working on, right? So the frame of, if your swarm robots is for dogs, the frame would inevitably inherit from the dogs. So that's what we're looking at. Now, embedded controllers is still roughly the same since it's aerial. The only thing now is we are going to have additional sensors because now we're not looking at just our robots. We want to be able to tell where other robots are. right? So there's this kind of broadcast thing where, say for example, you and your guys, 10 of you, you are working in a swarm. Maybe um Adams is at the far front, and you, for example, you have 4 friends behind Adams. You have no business with Adams' position. Adams is just the one giving direction. Your main concern is not to bump into the immediate person. So if the swarm robots are in a 2D plane, their concern would be the 4 people around them. If it's 3-dimensional, the number increased drastically, probably to 8 or so. So my point is, they need additional sensors that will not only tell their own location, but that of the ones like around them. And in that case, those additional sensors would have not been necessary if it was a single drone. Hence the innovation in swarm robotics, making swarm robotics to like stand out on its own. Now, another thing we would also look at is architecture, right? So each of the drones are identical. It's either they're identical or they're modular. I mean, you can have 2 different robots and you can hook it up in a way, make it modular, and it works. But let's assume they're all identical. So that's the architecture, like a lot of them. Now you're going to add something into it, into that structure, which is the propeller guard. The propeller guard is just like a cage, because the last thing you would want is, I mean, mistakes happen, and if one drone collides with another and the propellers meet, you lose the both propellers, and propellers are pretty expensive to fabricate. So this is why you have guards on some of the crucial parts, and then there are dampers on some joints of the drone in case they collide. It's a possibility. So when it comes to actuation, we've talked about structure. All of this is just the structure, the architecture, the way they are, the additional sensors and parts you would need. And then we'll talk about the actuation now. For actuation of swamp, you don't look at it from the eyes of one of them. If you see drone shows, when you look at drone shows, when you actually watch drone shows, you don't single out one drone. You look at the whole thing. You look at how they move, how they display numbers, how they do this. It's the whole thing you are looking at. So we are given that illusion of fluid motion as one, whereas we behind it, we know that, oh, this is actually individual distributed computations. And in a minute, I would probably explain roughly how that is achieved. So here we have actuator synchronization, which is one thing is moving, the other moves in a way. You just make all of them move in certain ways, and then the result is a fluid movement as the group. Same thing as what I was explaining. Now, this is the key. The key is each of the drones have their own control system or their control loop, and they run that loop at extremely high frequency, such that changes in state is seen as almost real time. And like when one just moves up, another moves up, like it's very fast that you do not see that they're actually moving one by one. So they are all moving like a nice synergy. And that thing now is sharing their information is the key behind this kind of robot systems. So you are going to have one robot sending its velocity, its position, and its orientation. It's going to like broadcast it on a wireless link. The one we used in Prague was a Zigbee. So you just broadcast, and that broadcast is short enough for the neighbors to get it, and not so long so that you don't have a lot of interference and a lot of power drain. So we have some rules that govern how they move, but this is a bit complex. But think of it as, if you want them to, you can set a rule: do not be 5 centimeter near another drone. So they can move, and once they detect 5 centimeter within each other, they space out. Now, if all of them should start at a distance of 1 centimeter from each other, if you arrange all of them 1 centimeter from each other and you turn them all on, they will all like spread out into 5 centimeter. And to somebody that is watching it from the outside, will be like, oh, they all moved out. Like they just did this nice come together and spread. But it's because you've defined a rule for them. The rule is not running somewhere as a centralized, it's running on all of them. So this one, as you turn it on, the first, all of them broadcasts their position and their orientation. As they broadcast, they also receive the position of the neighbors. And they know their position, they know the position of their neighbors, they are able to compute the distance. And the moment they all see the distance is 1 centimeter, they all engage velocities to like spread out. And this happens in a fraction of a millisecond. Sorry, fraction of a second, because you can have like you can have about um you can have about 2000 loops in 1 second. So roughly, yeah, roughly fractions of a second. So they now run so fast and like everybody just spreads out. So that is one thing. Another thing you can do is alignment. The same way you move in groups of your friends, the first person is moving forward. He knows where you are going to. All you guys need to do is, oh, we are following that guy, move with that guy. So they know who their leader is, and everybody just follows. That's different rules. And then there's cohesion, separation. There are a lot of more complex algorithms. So these are sensors, basically sensors we've covered before. We have control systems and things like that. And then communication and intelligence control algorithms. We're not going into that detail. We don't have that much time. My time is almost up. So let's look at maybe one last demo, which is for the control, which is for the swarm robots. So I can set 10 robots, and I'm going to have 10 robots. Again, I've set their parts, the same algorithm as the first one I showed you. So you see something. They all have fairly constant distance between each other. But in as much as they have this their uniform movement, to tell you that they are not centralized, they're not linked to each other, I can pull this guy out and it doesn't affect the rest of them. And say for example now, I gently tap this guy, he returns back. If I gently tap this one, he returns back to his position. So if I take this one outside, he flies back with more speed because he knows that he has been moved out of his position. So that's actually how swamp work. Whereas this guy is actually trying to, this one down there, he's trying to get up, but he can't get up because I took him out with too much force. So if I should delay the leader, okay, I dragged it too much. Okay, but either ways, that's the whole idea. You can take it out. Okay, now I've collided. So yeah, this is a simulation that is supposed to mimic real life. That's why there are a lot of crashing. Okay, so sorry, my laptop is freezing. Two simulations are running at the same time, and that's not a wise thing for me to do. But I'm doing it regardless. Okay, so that's for swamp robotics. I think I have only about 5 minutes left. And then this gives me my plot that shows me my chaos that I was causing. So we can look at autonomous robots because I mean, who talks about autonomy without talking about cars, the Teslas and the rest of them? So this is one. It's a Prisma robot. This is like a small one. This uses tractors wheels. This is a very simple model. You can see it's like everything is all scripted out, and you can literally see what makes it up. You see the structure. I mean, there's nobody that would see this that will not say it's that. Nobody can call this a humanoid. You see the structure. It has four wheels, even though it's not as big as a car, but you can tell that this is a mobile robot. And then you see from this place, you see the batteries on this side. You see the control system or like the processors. You also see a microcontroller. So this is for the high level stuff. This is for the low level stuff. You see a speaker. For some reasons, I have a speaker on this. This was for some form of communication, but you can also see ultrasonic as well as every other component that we've spoken of previously. So yeah, everything follows the same structure. My point is, you take out if you want to go on a general if you want to go on a general scale, these are the core. the 7 cores basically: structure, actuator, sensors, control system, power system, end effector, and communication. But you can take all of these and you would find out that robots are extremely diverse. So while you can say these are the building blocks, there are actually more that you can get if you look at it on like an individual level. So I think that clocks 45 minutes that was granted. Thank you very much for having me.
Okay, thank you very much, sir. Thank you so much for sharing basic knowledge and concept about robotics. We really appreciate you, sir. So the next session on this will be our question and answer section. So if you have any question, you can just I think you can drop it in the chat box, or you can do well to unmute yourself and speak. Is there anyone who has a question? Is there anyone who has a question? I think let me check. Okay, even if they don't have any question, I have a question actually. The question actually relates to somebody who doesn't have access to things that you have mentioned about robotics, like someone, let's say, less privileged, someone of less privilege. Like, how do how do one secure access to opportunities that makes one connected to this robotic aspect? Now that for one to build one's like one's project, or maybe one's innovation, or about something like this. Someone that doesn't have like access to things like this now, the dream can be killed. They
Okay,
might not really have
okay, so
the mindset of saying, I'm going to go into this robotics again. Someone like me now, it happens to me sometimes. So I just I just maybe I really directed my insight on this robotics. So how do one secure access to things that can help one build his own mindset about these robotics?
okay, so I'll put it this way: it's a mindset problem. It's a mindset problem, and I would give you this with somebody's story. I'm allowed to call the person's name because the person made the post publicly on LinkedIn. But then again, maybe I can keep it discreet. I saw his post where he was tagging. I don't know. I'm echoing. There's a reason why am I echoing? Okay. So I saw his post where he was saying this same complaint that you made, and his argument was he wants to really go into robotics, but he doesn't have access to the privilege. He doesn't do the da 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 da, and things like that actually tick me off. Reason being that for the people that actually know how me I started my whole tech and software thing, you would actually know that all of us na like, I mean, there are people that are privileged, but I was not, because nah. So this is what I would say: almost everything you need, almost to. Now there's a reason why I'm saying almost, because the first criteria is to have a laptop, and that is the greatest hurdle. So you must not have the best laptops, right? This particular guy made a post that he's running his laptop is on 8 gig, and he's using an i3. He gave the full specification of the laptops, and he said that his complaint was he feels he's less privileged because he wants to upgrade it to a better laptop, and he wants to buy hardware parts for robotics. And on LinkedIn, I'm usually a bit cautious with how I talk, right? Reason being that that's like a professional space. But at that point, I threw away all caution, and I told him he's not even a serious person. Like, he's not a serious person, frankly, and I'll tell you point blank. Reason being that I have showed you, I've showed you a robot dog. I have showed you autonomous robots. I can even show you a humanoid. I can literally show you a whole lot of things that I did not pay to get. That I did not pay to get. It's literally online. It's either, I mean, it did not come like um it didn't come already built. I had to do some work. But that's when you do some work, and that work is what you're supposed to be ready to put in. I don't know if you understand. Now, hardware is very expensive. You are very correct. But I did not start with hardware. As a matter of fact, you can do software completely without having to pay for anything. Python, C++, all of these are what? YouTube is free. I mean, data is expensive, but come on. You should maybe find a way to source data if that's the issue. But I feel if you are serious enough. Now, back to the story. I attacked this guy. I attacked this guy on LinkedIn, right? And after I did, based on I have this large follower kind of thing, a lot of people actually saw it. And then there's some people that supported that were like, oh yeah, yeah, that actually. And there's people that did not. So later on, this guy messaged me and he was like, he thought of everything and he said maybe he's the one being a bit lazy about things. And I should like actually like he's coming plainly that I actually wants to be mentored. Because for me to say he has more than enough to start, provided he has a laptop, it really touched him, right? So long story short, it's been 3 months and the guy is far better. Like he's confident enough to even make applications to US schools. Like he's far confident. A lot of the things that you need in robotics is more of awareness and knowledge than money. It's going to come to a point where it's going to be obvious that okay, yeah, you need money, oh, but it's not something that stops you. If you tell me it's hardware, like hardware you want to do particularly, then I'll tell you, you actually need money. But as my father will say, they use another man eye, they sleep. If you know that okay, it's tough for your side and you know to guide, instead of you to look at saying, oh, I want to start with hardware, I want to be buying expensive things. Now where your hand reach, you go first hand clothes. So you first start with software and you take it bit by bit. Say for example, in my own side, I didn't start my software life. I didn't start this whole robotics thing with hardware. No, I started with simple things. You watch YouTube videos, you try things around. So it's a very painful process. So you must put in the work, and I can guarantee you, even if you have the money and you're not ready to put in the work, you just end up buying junks and probably not using it. The same way, some philosophy say the cheapest thing to pay for is your gym subscription. The problem is, would you actually be able to put in that commitment to go every single time? So while I understand that there is a finance issue, I do not see it as something that limits you from entering. And if there's something I strongly believe, I believe that with sufficient hard work that you put in, you will go places. And I mean, all of us here know. I mean, somebody that we all know is probably Saka. I don't want to believe Saka came from a very wealthy family. I mean, I don't want to use wealth as anything because, see, I know where me I'm coming from, and I hate excuses like that. But Saka literally told the world a couple of weeks ago, and I mean, I can go on and on, but I hope by now you've probably seen what I'm trying to say. I can see one question that someone said, can we make 4 drones to be moving in one direction? Yeah, I mean, basically, you can do anything. Um, Hypothetically, you can do anything. So you just want them to be 4 in 1 line. Yes, you can do that instead of in circles. Yeah, you can do that. Thank you for the presentation. How do you go about robotics as a beginner? You see that question, eh? That question is a very valid question. Very valid question. Now, in the workshop I organize, Yes, yes, I can see your hand, BWeb Studio. I can see your hand, but like these questions came before you raised your hand. So in the workshop that I organized, as of people that go to that workshop, you find out that the most of the roadmaps you see outside are, how do I put it? They are not sequential per se, right? Almost nothing is sequential. There are times that I have a class and I'll tell my students, okay, see, there's more to this, but let's first know this. Because in order to fully understand it, there's another thing we need to know on one side. If you ever for some reason start by learning ROS, you probably realize that, I mean, why are we publishing from camera to why are we publishing from camera? Why is the motto subscribing? Why are we doing it this way? Why are we not doing it this way? And then you probably have to go back to robot architecture. And then you might be in robot architecture, and then you suddenly realize that for things to work a certain way, you need to understand some form of maths. And before you know, you're jumping into maths. And that's one problem that somebody complained to me. And he said, it seems everything is so connected that you don't know how to follow it. And the best way that I will answer it is start somewhere. And if you meet a stumbling block, divert to solve that block and ensure to return back to where you branched from. Else is a very, very deep descent into for more confusion. So as a beginner, you just have to start. I mean, when I started, it was also that difficult too. But as you keep on growing, and another thing that will help you is another thing that will help you is having a mentor. That's it's going to give you a lot of boost. Because for me, if someone asks, should I do this first and do this and do this and do this? I know because I have fucked around a lot. So I can say, oh, if you actually do it in this order, you're going to get some form of issues, right? And then I can give advice and say, okay, yeah, do this instead. So yeah, those are the things. You have to get the work done and you have to get mentor. So thank you very much for the eye-opening session. My question is, can one use simulation software to understand robotics better? Let me tell you something. CRS, Croatian, no, Czechia Robotics Systems Lab is the best laboratory in Europe for aerial robotics. They have a lot of drones, but never, like, you will not see them using drones to do robotics. Any form of learning, any form of lecture, any form of test, any form of anything remains in simulation. So it's only I see some kind of people say you cannot do robotics in simulation, you cannot do robotics without hardware, and to me it's bullshit. It's bullshit because most of the jobs I do is from software. I literally work remotely and it's all software. But people that know me. And I mean I do some hardware too, but like most of the jobs are software that I do. So what I'm trying to say is yes, simulation, yeah. Now, I'm not saying simulation is the only thing and simulation is perfect. No. I'm just opening your eyes because I mean this is probably the first time some people is seeing maybe a full robot in simulation, and the fact that you can move the robot around in simulation. Sorry, my laptop is actually freezing because I didn't run thing. So like either ways, you can run a full simulation, you can do almost anything you want. The code works and all of that. Problem is if you want to do a complete robot pipeline, like you want to go from idea to production. After you do all your simulation and everything works in simulation, you would have to now do what is called sim to real, which is to fine tune it to match real life, right? So yes, you can do everything in simulation. If no, could you provide a friendly textbook? Textbooks are not friendly, except you. I really don't know. I mean, textbooks are not really supposed to be friendly. Textbooks contain a lot of things. The textbook I might recommend to you might not be so friendly. So maybe um again it depends on the style. I'm not the kind of person I'm someone that prefer reading textbooks. I prefer reading textbooks than going to class or like than watching tutorials. But um I've recommended textbooks to some people and they're like it doesn't work for them. So I mean that's basically. Lastly, can we get slides for reference? Ah, yeah, sure. Provided you don't modify them. I mean, as it is. Okay, now is robotics all about humanoid? Ha, no. All the cars that are produced, I can say for Toyota, I can say for some other cars, almost from start to finish, they're all done with robots. None of those robots are humanoids. None of those robots are humanoids. So robotics cannot be all. As a matter of fact, the only reason why humanoids are popular now is because it's just because of ego. Because face it outrightly. I'm happy, please. I think I'm echoing.
Let me check.
Yeah, okay. Because face it outrightly, there's no real use case for a humanoid per se. And that is something I discuss with my friends a lot. I mean, we all know that most humanoid you see humanoid folding clothes, you see humanoid playing table tennis, you see humanoid doing sports, you see humanoid doing things, but there are more applications of robotics outside humanoids. You cannot put a humanoid and an industrial robot and tell me that a humanoid is better than an industrial robot. Humanoid just have hype. And the funny thing is, there are people sponsoring the programs. Like there are people that are really crazy about it. There's a lot of money in it. So I and my friends, we can laugh all want to laugh and say humanoid now just like that. But if work come for humanoid with the kind of money they attach to it, you'll still see us working on it. So that's just the thing. It's just like this nice hype that is around it, and it's doing very well too, by the way. So I see the reason for the hype. Now, what technology used in AGV for lifting goods? That's a very ambiguous question. It's a very ambiguous question because I want to assume you are talking of autonomous ground vehicles, and if you are lifting goods, I don't know if you want to lift it from ground all the way into the payload, but with assumption that that's what you want to do, a hydraulic system will be better depending on the payload. So hydraulic system is what I would answer that, but I'm telling you that that's ambiguous. And how can we get textbooks in Nigeria? I don't know. This is something that I think you can just search for online. You can buy textbooks online. You can go to your library. I know there's a library that has I've forgotten which of my students saw that, but one very nice textbook by Bruno Siciliano is actually in his library. So if it's in your library, you can actually buy it. Also, you can order from Amazon. It will take like 2 weeks, but it's expensive. I think it's expensive. Can probably run into about 80,000, 100,000. But again, why get the textbook hard copy if you want soft? If you can get it soft copy, so it depends on you, Sha. Okay, Vincent, your hands are up, please. What's up?
Which person?
And I
Can
can
you
say
speak?
Vincent.
If you have a question. Oh, maybe it looks like person cannot have access. How maybe we can get through the person to ask our question later.
All right,
Maybe
no
on our
problem.
platform. I'm going to contact you. Okay, so before we put an end to this meeting, I would love to recognize the presence of our RAIN team lead, the person of Saka. If he has any addition or any comment, I don't know if he's here. Okay, I don't think he's here. I just checked through now. Okay. Okay, once again, I would love to appreciate our speaker for today's session. Sorry, I wanted to ask a question. Okay, okay, yeah, speak. We're waiting for you. Hello, can you hear me?